The next 2 units of this course will deal with differential equations. The unit of today consists out of 3 videos. In the first video, I will introduce you to the concept of differential equations and show you basic examples and strategies of how to solve them. In doing so, we will also see the limitation of this approach. And in the second video, we will hence develop a general theory for a special class of differential equations, namely linear systems of first-order differential equations. And in the final third video of this unit, we'll then give a practical approach of how to explicitly solve a specific linear system of first-order differential equations. Let us start with some definitions and a discussion of what a differential equation actually is. Now, in a nutshell, a differential equation is an equation which doesn't only contain variables, but functions, and not just functions themselves, but also derivatives. That's why it's called differential equation. Now, in this unit here, we will always denote functions here like this, namely x of t. So we are considering functions that depend on one parameter, in this case t. Note that this is just choice how to write the notation. So we could just as well have used, for example, y of x, which we'll actually do in the second unit about differential equations. So here x of t, that of course the notation comes from a physics background, where, for example, we would be looking at the dependence of a quantity on time, t. So that's why we have t here. Now, we also have to take derivatives, as I told you. We will introduce a shorthand, namely the first derivative of x with respect to t is denoted as x dot, and the nth derivative of x with respect to t is denoted by x to the power of, in brackets, n. Now, an nth order differential equation is an equation that involves derivatives up to nth order. And in general, one can write those such that we have the nth derivative of x with respect to t equals to some expression, some function that depends on all the lower order derivatives, as well as the function itself, and possibly the time t explicitly. Now, this is a generic form. We'll then actually later look at some specific examples. What's important to realize is that differential equations are always accompanied by initial conditions. Those are actually then used to make the solution unique. Again, we will look at this in the examples. And in general, if we have an nth order differential equation, then we also have in total n initial conditions, which where we specify at some time t0 the n to the minus 1th order derivative up to the function value at the time t0 itself. Let us now a little bit more specific and look at some examples. And the first example we want to look at is a simple first order differential equation. So we only have the first order derivative here in this equation. And it's a very simple equation. It says namely that x dot equals to a function f of t. So it only depends, the right-hand side only depends on the time t itself. Doesn't depend on the function value x, for example, here. Now, basically the main trick that we'll always be using in all of these explicit examples that we're doing is that we basically want to integrate the differential equation to find the solution, because the idea is that if we do the integral of x dot of t dt, the indefinite integral, we get x of t as the solution. So what we actually see here for this particular equation, if we integrate both sides with respect to t, then we actually get x of t equals the solution. So how do we do that in practice? So we need to integrate the right-hand side, and to that end, let us define the antiderivative, capital F of t, which is given by the indefinite integral f of t dt. So the integral where we don't put in explicit boundaries in the integral. And well, it's called the antiderivative because df dt equals to f of t. With this, we can now easily write down the solution, which is now given as x of t equals to capital F of t. Well, that is one solution actually. It's not the most general solution of the differential equation. And what we need to do to get the general solution is to add a constant c to that expression. Because what you see is if you take the derivative with respect to t on both sides, we still end up, if I take the time derivative here on both sides, it still end up with this differential equation here, because the derivative of c with respect to t, which is a constant, just gives 0. So this is just related to the fact, that the antiderivative in general is only defined up to a constant. Now, this constant here, we need to get the most general solution. When we have initial conditions, the initial conditions will then actually fix the particular value of this constant. And let's have a look at this for this particular example that we have here. Namely, we have a specific example, x dot of t equals to t, and the initial condition x of 0 equals to 2. So it's a first order differential equation. We have exactly one initial condition, and that involves the function itself. Now, this is of course easy to solve now, because for the differential equation, we just need to integrate both sides. We get x of t equals to 1/2 t squared. So that is the integral of t plus c. Now, to obey the initial condition, what we do is we plug in the value of t, which is in our case 0. So we want to look at time t equals to 0. Now, if we plug in t equals to 0 in this equation, the first term that we have here, that is 0. So we just end up with this being equal to c. And this, according to our initial condition, needs to be 2. So here we see we directly fix the value of c with the initial condition. And we get the complete solution, x of t equals to 1/2 t squared plus 2. Now, this was a very basic and very easy class of differential equations. Let's go a little bit more complicated. So we get the next category of differential equations that we can still solve very explicitly. And that is now basically the opposite. Before we had that x dot equals to a function of t. Now we have equals only to a function of x. So of course it does depend on t implicitly here through x of t, but it doesn't explicitly depend on t. Now, how can we solve that? We apply a little trick. And the trick is we bring f of x of t to the other side. So we divide by f of x of t. So we get x dot of t divided by f of x of t equals to 1. And this we can now actually solve if we now make another definition. Let us define capital F of x. Now, before we had f of t, now we have f of x equals to the indefinite integral of 1 over f of x dx. So why is that useful? So first of all, well, we do know that df dx equals to 1 over f of x. And well, what we actually can now show easily that with this definition that if we take the derivative with respect to t of f of x of t, so well, we have now put the function x of t inside the function f of x. So when we take derivative, we need to apply the chain rule. That gives us df dx at x of t times x dot of t, which is x dot of t divided by, because that's how capital F was defined, divided by f of x of t. So we see directly now that we get the left-hand side here, and we know that this should be equal to 1 according to our differential equation. But now we see again we have a total time derivative on that side. So it's again easy to take the integral on both sides, because from this it immediately follows that capital F of x of t equals to t plus a constant. Now, this is the implicit equation for x of t. It will not depend on the exact form of the function capital F, whether we can solve for x of t, but in principle, to get an explicit solution, we need to solve for x of t to get the final solution. But sometimes even having an implicit equation, as we have here, could already be useful. But in the cases that we are going to consider, we will always be able to solve for x of t. Again, let's apply this to an example. And the example equation that we look at is that x dot equals to lambda times x. So here, this on the right-hand side, we have our function of x being lambda times x. Now, the first thing that you might notice here that I became a little bit sloppy, so I didn't write anymore, x of t here on both sides. I just write x dot equals lambda x. This is just a shorthand notation in all of these differential equations. We actually know that we have to deal with a function. The x dot actually, that definitely gives away that this is the case. So it's okay if you do it like this. Also, if you feel a little bit insecure, then better actually write it out explicitly as a function of t. Now let's apply the trick that we just defined to this particular equation. We get x dot divided by lambda x equals to 1. We need to calculate capital F of x, which is the indefinite integral of 1 over lambda x dx. Now, the integral of 1 over x, we know that this is the logarithm. Now we just need to take care of the fact that there's another constant here. So what we get in total is a logarithm of lambda x divided by lambda. So this 1 over lambda just comes from the chain rule when we do this integration. So with that, we can now put this in our equation. So we know now that the logarithm of lambda x 1 divided by lambda equals to t plus c. Then we multiply both sides with lambda to get logarithm of lambda x equals to lambda t plus lambda c. And then we go further. We need now to solve for x. Now the inverse function of the logarithm is the exponential. So that's what we need to take on both sides. And then we get lambda x equals to e to the lambda c times e to the lambda t. And with that, we can finally solve for x itself. So x of t, you see now I restored the notation as a function of t, equals to 1 over lambda e to the lambda c times e to the lambda t. Now, I told you before that, or we saw in the previous example also, that the coefficient c, this constant c, is determined by the initial conditions. Now, what we actually see is that here, there is a whole expression of constants that comes about. And for notational convenience, it can actually be useful to redefine those as a new constant, which here I call C0, so that we can write a more compact form of the final solution as C0 times e to the lambda t. What is useful to notice here is that in this whole derivation, I only did basic algebraic operations, and I never specified what the value of lambda is here, for example. And actually, this whole derivation is valid for both lambda real or complex. So this is a useful observation. So we now looked at cases where the right-hand side of the differential equation either only depended on t or only depended on x. Now let's actually see if we can solve a situation where it depends on both. And it turns out that we can actually easily generalize the situation that we just had by having on the right-hand side f of x of t times a function g of t. So now here on that, in this case, the right-hand side depends both explicitly on x and on t. Now, this is not the most general form. This is only for a product, but still it does depend on both things. And it turns out that the trick that we were just been using before also works here because, well, what we can do again is we can just bring f of x of t to the other side, getting x dot of t divided by f of x of t equals to g of t. And in that form, you now see, what we did before is we integrated the left-hand side. The right-hand side was just 1, but now it's a function of t, but we can still integrate that over t. And then we get a generic solution also for that case. So let us define as before, capital F of x equals to integral 1 over f of x dx. We also define capital G of t equals to integral of g of t dt. And with that, using our previous results, we can simply rewrite this equation as d dt f of x of t equals to g of t, and thus we can solve this to give f of x of t equals to capital G of t plus a constant. And as before, what we need to do is we need to solve for x of t. So basically the only difference is now you need to solve 2 integrals instead of 1. Let us again apply this to specific examples. So the first example is here. We have a right-hand side, which is a product of t. So this is what we were defining as g of t before. So this was g of t times x squared, which is what we defined as f of x before. Now, let's apply our trick. So we get x dot divided by x squared equals to t. We need to compute the integral of 1 over x squared dx, which we can easily find. So we know that 1 over x, the derivative of 1 over x with respect to x is minus 1 over x squared. So the antiderivative of 1 over x squared is minus 1 over x. And then we know, so this is the integral of the left-hand side. And the integral of the right-hand side can also be easily done because this is simply 1/2 t squared plus c. So what I actually did here is I actually was a little bit sloppy in my notation because you see here, I do this integral over x, there is no t here. But what we of course know what it means is what we were just writing on the page before. So we have to understand x as a function of x of t, and basically what we didn't write here explicitly is the x dot that we have in this expression up here. So again, you can do that if you know what you're doing. And for this specific example that we have here, this is the way how we can solve that. Again, if you feel uncomfortable with that, then just write everything out very explicitly, keeping the t dependence always there. Now, for this particular case, we can actually easily solve for x of t. So here we find that x of t is now given by -1 divided by 1/2 t squared plus c. You can further simplify this equation if you multiply both numerator and denominator with 2. Then we would get a -2 here and here 2c, which we could redefine as a c0 again. But it's not essential. So this is just to make it look nicer, but the previous solution was just as good. Now let's look at the second example. And this is the example that I'm showing here. That is that x dot equals to a general function g of t times x. So this is an interesting equation because it's a so-called linear equation. So x only enters linearly. And we look much more into these equations in the following. So here we'll just apply our specific recipe to solve that one. Later we'll actually learn more about these kind of equations. So again, let's apply our trick. And we have x dot divided by x equals to g of t. We need to integrate both sides. The left-hand side gives us logarithm of x, because we have to integrate 1 over x, equals to capital G of t, the integral, the indefinite integral of small g of t, plus the constant, which again I can easily solve to find x of t equals to e to the power of c times e to the power of capital G of t. And I can again redefine this as c0 times e to the capital G of t. So, we already had a specific case before where we had here for G of t, the constant lambda. Remember that there we actually had as a solution e to the lambda t. Well, that is actually just what the integral of lambda is. You just get lambda t. So this is the generic expression where you see that in the exponent, you have the indefinite integral. Now, these were all examples of first order equations, as I told you. Actually, in physics and engineering, in many cases, you also encounter higher order equations. For example, second order differential equations are very common. So it might sound natural now to go to higher order equations, such as the second derivative of x equals a function that only depends on x, for example. So we could do that, but it turns out that becomes quite tedious. So it's not fun to do that. Actually, what we're going to do is we now actually take a step back and we'll actually now focus on a specific class of differential equations, namely so-called linear differential equations. And what we'll do there is we will derive a general theory for these linear differential equations. And this will be the topic of the next 2 videos.